I would like to introduce Piotr Kulczakowicz, the director of Quantum Startup Foundry in College Park, Maryland.
Thank you. Thank you, thank you, thank you. This is about presenting companies in our network, QC82 and NanoQT. But I want to start with a few words of introduction for the startup Quantum Startup Foundry in College Park, Maryland. We are part of the University of Maryland. This short story is going to be really the story of geography. If you look at this map, we are at the center of probably the highest concentration of organizations and institutions working on quantum technologies. The highest concentration of talent in quantum is in this region. University of Maryland is right at the heart of this region, and I bring this map to illustrate that we are just 8 miles from the White House, from the Washington Monument, from the mall. This means that a lot of government customers are also in this region, right? And UMD is a little bit unique. It's really outward looking. So if you look at this map, it's the University of Maryland is on the left side, and on the right side we have Discovery District. So if you look at University of Maryland, this is where we have over 200 PIs working on quantum. Add to that postdocs, doctoral students, undergrad students. We have very vibrant undergrad quantum association. Lots of things going on. We have 13, I think that's the last count, institutes dealing with quantum. I will name just a few: Joint Quantum Technology, which is a partnership between University of Maryland NIST, or Quantum Technology Center located in the newest building on the campus, the white one in the middle, called the Idea Factory. And then on the other side of the street of Baltimore Avenue, you have Discovery District, where we have IonQ, where we have QLab, where we have government institutions such as NOAA, where we have Quantum Catalyzer. This is a private incubator, and one of the companies in the incubator, they won yesterday's competition, pitch competition for startups. We have a lab advanced. I think we have a little bit of feedback. Anyway, and the whole place is developing and really fast. And in the middle of that, in between University of Maryland and Discovery District, there is Quantum Startup Foundry, which is an incubator, accelerator, and a landing spot for quantum startups and businesses in Maryland. This is a place to come and be part of our very rich quantum ecosystem. We have a number of umbrella programs going on. What's really different about Quantum Startup Foundry is that we are really agile and adaptive to changing market conditions. We really cater to these individual companies and their needs. A couple of samples. Pre-traction program is focused on earlier stage companies. 3 of companies from our cohorts got SBIR, STTR funding. Traction is really the core program where companies like QC82 and NanoQT want to become part of the Maryland ecosystem. We work with them, provide space, connections, and such. Capital connections kind of obvious. We do quantum investment summits. We connect startups with investors. And we also run Discovery Fund out of University of Maryland. And one of the companies presenting after me actually got investment from the Discovery Fund. And finally, very important partnerships. The last slide I want to show is again, the view of the campus. And you can see a lot of construction going on. And this is to illustrate that the place is growing, it's booming, and it's becoming, really the heart of this capital of quantum capital region. If we were to add all the money that went into this, into the institutions and the organizations, I don't know what the number would be, but it would be very high investment into quantum in general. I'll stop here and I'll bring the first company to present, QC82. is based at College Park at our foundry. They are in photonics. They are building a photonic quantum computer. Paul Renault is a quantum architect for the company, and he will present and showcase a little bit about QC82. Welcome, Paul. And I'm going to start your presentation in just a second. Here you go. And the mic is yours.
Okay, thank you, Piotr. Okay, thank you. So, yes, my name is Paul Renault. I'm working for QC82 as a consumer architect. Before that, I was a postdoc at the University of Virginia, and also before that, I also did my PhD in Paris in the Kastler-Brussels laboratory. So QC82 is a hardware company, and our goal is to build a scalable room temperature integrated photonic quantum computer at telecom wavelengths. So here on the top left of the slide, you can see some numbers. This is our target number for quantum computer it's a target for the long-term period. So our goal is to build a quantum computer with 1 million physical qubits, which will correspond to something around between 100 and 1,000 logical qubits. And also we want to build a machine with which will be able to run between 1 million and 100 million gates. And also at the top of that, we also need to be scalable. So these numbers are very ambitious, but we believe that with this kind of numbers, our quantum machine will be able to solve a high-value problem. So here on the right of the slide, you can see some application of future quantum computer, such as simulating chemical reaction or material science. And then the question is, how can we address the problem of building a quantum computer? So at QC82, we have chosen to work with a continuous variable physical qubit. And more specifically, we want to generate GKP states. So because we believe that these states are actually well suitable for quantum error correction code. And also one of the main challenges today in the quantum computer field is the scalability. At QC82, we want to tackle this problem by getting rid of any cryostat in our quantum computer. We want to operate at room temperature. So some highlights about the company. So QC82 started in 2022. It was co-founded by 5 people: Hussein Zaidi, the CEO, and also 4 professors from the University of Virginia. Right now, we are located in College Park, as Piotr mentioned. So we have chosen the campus of University of Maryland because we believe this is a nice place for the development of a quantum startup. Also, for example, there is the Quantum Startup Foundry with Piotr, who is always very helpful. And also, right now, we are a team of 4 people working full-time for the company. There is also 4 scientific advisors and 2 business advisors. We are currently in a seed phase, so we have raised money from VC and also we receive a grant. And during this seed phase, we have submitted already 14 patents, and 4 are also in preparation. So these patents are based on the research we are conducting at QC82. There is an experimental side on the research, and also a theoretical one. Regarding the experimental research, it is done in collaboration with the University of Virginia. So there is what is this research? So we are actually designing and fabricating integrated photonic components. We want then we project to implement in our quantum computer. So until now, we're focusing on 2 components. So the first one is a photon detector operating at room temperature. So it's actually a SPAD working at 1550 nanometer. So the advantage of this detector is like it's working at telecom wavelength, so it's low loss, and also it's fast. It's working in the megahertz. And also, like, the idea is to implement this SPAD within like a segmented detector to actually make a detector which will be able to resolve like the number of photons you detect in your optical mode. The other component we are working on is a quantum source, because it will be like the first component in the circuit of our quantum computer. So this work is done in collaboration with a group of Shui. So Shui with his team has already demonstrated the integration of an OPO cavity, which can generate a squeeze vacuum state. So in this cavity, 70 frequency modes were resonant, and so right now we're also like working on the integration of the OPO cavity and the homodynamic detection on the same chip to reduce loss for the squeezing measurements. And then on the theoretical side, we are working on the quantum computer architecture. So the idea is like to determine what are the parameters do you need on your component to then like be able to generate a good quality JKB state which would be like enoughly good to then like perform quantum error correction. So on this side, we have like we got recently like preliminary results. We are about to publish, so it will be like the archive paper is like almost ready. It will be like published at the end of the month or next month. So now about the team. So as I told you, there is 4 people working full-time for the company. So on the left, these are the people on the left of the slide. We have Hussein Zaidi, the CEO of the company, who couldn't be here today. Sorry for this, he's traveling. We have also Rifil Puzer, who is a senior scientist, former PI at Oak Ridge. We have also Patrick, PhD from Munich, also he was also from Bristol. He worked on the quantum error correction code on myself. We have also 4 scientific advisors from the University of Virginia. So Joe and Andreas, they are working on the photon detector, and we have also Shu working on the quantum source. So Joe, Andreas, and Shu, they are from the engineering department at UVA, and we also have Olivier from the physics department, so he's an expert in continuous variable quantum optics. And we have also Stuart and Imran, who are helping us on the business side of the company. They are helping about like for the commercialization of our components, and also on the VC relation. So, not on the scientific part, all the people are PhD. And we are also like very glad at QCT2 that we have also a very, we believe, good scientific advisor. The people like from UVA, they are actually like in their field recognized as world experts. So it's very helpful for the company, especially if you want to be like ambitious in a very competitive field. So the company until now has raised more than $1.5 million. We are also involved in the DARPA US QC program to build a quantum computer, and we have also like a partnership with UMD on the state of Maryland. We have a collaboration with the engineering department at UMD to also design and fabricate components for our chip. And we also received like a grant from the state of Maryland to build a lab on the UMD campus to fabricate components. So this is like the next step for us, building the lab to then fabricate components. We also are planning to raise more money at the end of the year, or at the early 2025. With this money, we'll be able to hire more people and also accelerate research and development. And yes, because we have also like in mind to commercialize photonic components we are like developing right now. So this is the end of my talk. I guess maybe you have the question later, or
we have a minute for a question or two to Paul. And if there are no questions, the next presentation is Masashi Hirose, and he's the CEO of NanoQT, or Nanowire Quantum Technologies, which is another company in our network. And I'll let him speak to what they're up to.
Thank you.
Masashi.
Good afternoon, everyone. My name is Masashi Hirose. I am a co-founder and CEO at NanoQT. Today, I came from Tokyo, Japan. This is my third time attending QWC, and it's a great privilege to be a part of central gathering for quantum initiative worldwide like this. And today, I'm very honored to speak about NanoQT, representing startups at QSF in University of Maryland. So we are actually very early startup, focusing on really like hardware challenges, especially integrating multiple computing units by optical fibers. And our approach and technologies is quite unique in the market, and I'm very excited to share in the following. Here, right? All right. So before we deep dive to the technologies, let me briefly explain about NanoQT, because I think many of you may not be familiar with us. So NanoQT is founded in almost 2 years ago with a research developed by a professor at Waseda University. And we are actually the first startup in Japan in quantum computing hardware domain. And as you know, there are already a lot of like startups in hardware domains using like different approaches such as superconducting circuits, ion traps, neural atoms, etc. But our approach is completely different from the incumbent players. We use a technology called cavity QED. QED stands for quantum electrodynamics. And cavity QED has been well known in the academic community for decades. However, the commercialization has not yet been done, especially because there is a lot of challenges to engineer the ideal cavity for quantum computing purpose. So we overcome those challenges by a decade of research in the university, and also unique and robust a fiber optics value chain in Japan. Lastly, while we are born in Japan, our aspiration is to be global. And right now, we operate both in Japan and the United States. So in the last 2 years, we have significantly grown in terms of patent portfolios, talents, and also capital raisings. What set us apart from the other players is that we are deeply connected to quantum ecosystems, both in Japan and also US. And also we are backed by venture capitalists, both in Japan and the US. And also we have a strong support from Japanese government and recently from also Maryland's State Department. Right now, most of the technology developments are happening in Tokyo, Japan. But our headquarters in California side, in Palo Alto, where we have a support from Japanese government. And recently, thanks to support from QSF and also Maryland Department of Commerce, we opened an office in Maryland in the QSF to really accelerate R&D, especially around error correction algorithms development. In already last couple of months, we have actually, thanks to support from Piotr, we are connected with already a couple of faculties in UMD, and we already have a couple of ongoing discussions on collaborations with them. Right, so from here, let me deep dive the technologies. So the challenges that we are tackling is really how we scale the hardwares, especially the increasing number of qubits. And as you know, the demand for more qubits is actually accelerating, especially because error correction algorithms have arrived, and more qubit leads to better qubits. I mean, reduction of rate. Right now, we made a really great progress in the last decades, and the state-of-the-art quantum computer reaches like 1,000 qubits. But we still need a factor of hundreds and thousands scale up in terms of number of qubits. Given that needs, the current approach, mainly like monolithic structure, where their effort is basically to maximize the number of qubits in the module, faces significant challenges from the hardware perspective. For example, like wiring problems in superconductor circuits, laser powers, crosstalks, etc. So to really like scale up in a sustainable way, we need to make a transition from monolithic structure to the modular structures via optical fiber. And the modularization via optical fibers brings us to have another dimensions to scale up. And also, in addition to the scale-up method, actually, so the modularizations integrates the quantum communication, which is right now largely decoupled from quantum computing because there is no hardware commonality between these two, that's why actually the application of quantum communication is really like limited. So the modularizations via optical fiber really integrates the capabilities of quantum computers and also quantum communications. But how can we make this transition from the monolithic structure to the modular structures? There are actually a couple of challenges. Number one is a reliable. We need to really to realize the reliable photonic signal conversion. That's number one. And number two is, can we really realize the high, fast sync rate, especially like how fast we can create the entanglement at different locations, and fast enough to catch up with the QPU clock rate, which is typically megahertz or even higher frequencies. So in order to solve those challenges, we offer two solutions. So number one is to the high bandwidth quantum interconnect, fully compatible with a neural atom QPU. And this enables the distant QPU to communicate without sacrificing local clock time using optical fibers. The second, in the right-hand side, we are also developing a quantum repeater, which is the crucial enablers to scaling the quantum computing and also quantum communications. Unlike the current efforts in hardware development of quantum repeater, such as a photon source or a quantum memory, our repeater design is really based on QPU, offering features otherwise not available, such as full capabilities of entanglement operations, such as the entanglement generations and also distillation. And our repeater also has a qubits with a long coherence time, telecom wavelengths, and a gate operation available. So those functionality expands the possibilities of quantum communications and also computings, especially in terms of applications. And yes, so we recently published a technical paper on how we realize the quantum interconnects, and that's posted in the archive. And if you are interested in technical aspects of our technologies, please visit the website. Right, so as I mentioned, to realize the photonic modularizations, reliabilities, and rate, like megahertz above rate, is crucial. And let me explain how we overcome those challenges in our technologies. So the current state-of-the-art entanglement generation device is mostly based on the free space design, where we can get the, actually the 10 or 100 hertz range, especially because the qubit in the free space emits the photon in a really incoherent way because of the spontaneous emissions. So photon collection efficiency is quite limited. To that issues, we install the cavities, we call it nanofiber cavities in the systems, which significantly improve the photon collection efficiency, at least a factor of hundreds. However, there is now the drawbacks of neural atoms kicks in. The neural atoms requires a long, actually, preparation time, like 100 microseconds initialization, loading, which actually makes the duty cycles quite low in the process. So in order to overcome those challenges, we massively scale the number of qubits by using optical tweezers, and also integrates a number of cavities in one modules. By doing this, we parallelize the systems, and thanks to time multiplexing, we can gain another factor of hundreds of thousands improvement to really reach the megahertz rate of entanglement generations. Yeah, so let me a little bit explain the implementation plan. Here is a technology roadmap. Currently, we plan to build a prototype to demonstrate distributed quantum computing systems integrated into the neural atoms to the arrays before FY27. Before that, we test in small modules. FY26, we simply combine like 2 cavities with a few qubits to demonstrate the basic protocols of quantum repeaters. Right now, we are developing the first prototype in actually 1 modules. And this is an overview of POC machine, which is pretty much like a neural atoms quantum computers, but we have a cavity inside. And you see that there is multiple neural atoms trapped by optical tweezers in a proximity to a nanofiber, where the neural atoms are coupled with an evanescent field from the nanofibers, forming the cavity QED systems. And you see through the cavity, as a signature of coupling between neural atoms and cavity, we see actually the state of a single atoms, not from free space, but through a cavity. So lastly, as moving forward, we have completed a technology validation phase with the seed round financing, and now preparing to build the proof of concept machines to demonstrate the quantum interconnect and quantum repeater. And we're about to launch the next financing in Series A to build the prototype here in the US. And we're also seeking for collaborators, especially to think about the applications or use cases utilizing our hardwares. And lastly, yes, we have a couple of job openings, both in US and Japan, full-time or interns. And if you're interested in it, please visit us, the website. That's all. Thank you very much.